So we're continuing talking about special square matrices. So right now let's just talk about some properties of diagonal matrices. So the first thing is that diagonal matrix. So if D is a diagonal matrix, then that means all of the interesting stuff just falls along the diagonal. So I'm just writing it like this, but this implicitly means that everything else is a zero. So sometimes you just write a big zero, or you can leave it blank. So this has to be an n by n matrix, because there's first diagonal entry, second diagonal entry, finally the nth diagonal matrix. But anyways, so if you have a diagonal matrix written of this form here, then you can do matrix multiplication. So you can do d times d, or d times d times d, or you can do d to itself as many times as you want. So in particular, you can do d to some power, and a diagonal matrix to some power is also a diagonal matrix, and the diagonal entries are obtained by just raising each of the original diagonal entries to the same power. So that's the first property of diagonal matrices. Second property of diagonal matrices is that if none of the diagonal matrices are zero, so if every entry is interesting, so non-zero, then the matrix is actually invertible. So D is invertible, and the inverse matrix is also diagonal, and it's just the diagonal obtained by taking the reciprocals of all of the entries. So we couldn't do this. This wouldn't make sense if one of these entries are zero. So the assumption here is that D1 is not zero, D2 is not zero, D3 is not zero. So none of these diagonal entries, Dn, can't be zero. If they're not zero, then all of these are perfectly acceptable. You can take the reciprocal of any non-zero number. So just as an example of, so if A is the matrix, say 1, say 3 minus 2, or sorry, I'll say D for diagonal. So if D is this matrix here, so I'll put in all the zeros since it's only a 3 by 3 matrix, then D inverse is the matrix 1, 0, 0, 0, 1 third, 0, 0, 0, minus a half. So that's how you obtain the inverse of a diagonal matrix. You just take the reciprocal of all of the diagonal entries. And for example, D squared would be the matrix 1, 0, 0, 0, 9, 0, 0, 0, positive 4. And so that's how, so diagonal matrices, they're pretty easy to calculate the inverse, and they're very easy to exponentiate. Now there's a third property, which is how diagonal matrices act on other matrices. So if D is D1, Dn, so this means it's an n by n matrix, D, and if M is any n by m matrix, then we can multiply dm, so this is now an n by m matrix, because we did n by n by n by m, and the resulting thing is n by m, is obtained by scaling the, say, jth row of m by dj. Is obtained by scaling that matrix by dj. So it's kind of an easy thing. So for example, if D is the matrix 3, 0, 0, 2, and if M is the matrix 1, 2, 3, 4, 5, 6, then we can multiply these two matrices, D times M, And this has the effect of, we're just going to triple the first row. So what does this say? This says what you do is you multiply the jth row by dj. So in particular, you'd multiply the first row. So this first row is just going to get multiplied by that. And it says that the second row gets multiplied by that. So it's very easy to do matrix multiplication. So it's easy to multiply a matrix by a diagonal matrix. So this just becomes 3, 6, 9, 8, 10, 12. So diagonal matrices are easy to multiply.